So this is one of the controversies where you can go swimming during the coffee break. And I hope some of you did. So we're waiting 2 more minutes. No, in fact, it is already 1/2 Don't know if we wait for the organizers. So maybe I will start. So if you like, a few people still arriving. So thanks for. So I hope everyone had good swimming or at the beach. Or, okay. Maybe some of you were able to find some coffee in town, or just near the beach. There are several places where you can find coffee. I wonder if we'll survive. How long we will survive without coffee? Yeah. Yeah. Okay. So this session was not written as an exercise session on the program, and I did not plan to do exercise sessions. So we agree on that. So I will continue the lecture, and we will do the exercise tomorrow. Exercise session tomorrow. So I rewrote some of the expressions now full. I filled the expressions. I always wrote them with t equals 1. So h bar is 1/n in these examples. So I have now exactly the good values where gamma is given by this formula. Can you hear me? Yeah? Okay. I just wanted to make the parallel between this that came from matrix models and what I started with this morning about quadrangulations counted by Tut. Tut found this formula here. And you see, for example, the parameter gamma square is, sorry. So I use the variable, I call it t tilde 4 instead of t4. You see this formula, they look very much like these ones, They look very similar, except that, except some sign. For example, here you have t2 square plus 12t4, whereas here we have minus 12t4. In fact, the counting of quadrangulations corresponds to a random matrix problem, but with t4 negative. And t tilde 4 is minus t4, and t2 equals 1. So which means a potential which is upside down. So it's not bounded from below on the real axis. So you cannot choose gamma. I mean, if you basically this really looks like a particle matrix model, but not for Hermitian matrices. You cannot choose gamma to be the real axis. Just not. I mean, it would not make sense as a Hermitian random matrix. Gamma cannot be chosen as a real axis. Apart from that, the formulas are the same. Well, in fact, there is a way to actually represent quadrangulations as a true random matrix, but you have to choose some path in the complex plane, and this is not so natural. There is in fact, I think, okay, the link between random matrices and quadrangulations or counting maps was, well, when the physicists discovered it in the 80s or 70s, 80s, and 90s, it looked really great, this link. It would give the impression that it was easier it seemed that solving random matrices was easier than counting triangulations, than solving combinatorial problems. Nowadays, we understand that it's a little bit the opposite. It's easier to solve combinatorics than doing the analysis of random matrix model. In fact, it is easier to do random matrix model only if you assume that the topological expansion holds. But proving that it holds is really very hard. And also, you have to work with random matrices in a very strange setting where your matrices must have eigenvalues on some contours that are not real axes. And from the point of view of random matrices, it's not natural at all. And in the end, you can do everything with combinatorics without ever mentioning random matrices, and maybe it's easier after all. Well, working with random matrices is nice because somehow it gives intuition, but just take it as intuition. Don't take it as proofs of theorems. Okay. However, the formulas are really the same. So I will erase that. So it was just to recall that triangulation is the same thing as quartic matrix model, but changing the sign of T4. So, this is terrible. So now I wanted, so I wrote the formula here. So this is basically the same ones I wrote this morning, but with the correct coefficients everywhere. I will say a few words about really how you get them. But first, let me say that, okay, this is the formula we got. So this is W01 also of X. So this is the formula we got. It satisfies this algebraic equation with this polynomial. Okay, it's a degree. So the equation is of degree 2 in the variable y and degree 3 in the variable x. This is the solution. And corresponding to this resolvent, expectation value of resolvent, corresponds an expectation value of the density of eigenvalues, which is basically the discontinuity of the resolvent divided by 2 pi I. Yes, so I'm not sure of, is it 4 pi or 2 pi? Okay. But nevertheless, it looks typically like that. So you see it's a square root multiplied by a polynomial of degree 2. And it looks like that when this polynomial has no zero between the two endpoints, which corresponds to the value T2 larger than minus 2 times square root of T4. What happens at T2 equals, so what happens when T2 equals square root of T4? It is exactly that. So it has a 0 exactly at the origin. It looks like that. It's still a positive density on the real axis. But if you would continue with T2 smaller minus 2 square root of T4, you would find that, which is not a positive density on the real axis. It takes negative values, which is impossible if it was the expectation value, if it were the expectation value of an eigenvalue density of a random matrix, this would not be possible to happen. So it means that our hypothesis that we had the Gini zero curve somehow fails in this regime. So to go back to what I said before, I said that for given values of T2, T4, and on all of this, we have some good paths and bad paths. And basically what happens is that in this regime, the real axis is a good path. In this regime, our hypothesis that the real axis is a good path does not hold anymore. So it ceases to work in this regime. I will show you now what is the good spectral curve in this regime for the real axis, but it's not a Gini zero spectral curve. let me give you directly the formula. Sorry. In the case T2 is strictly smaller than -2 square root of T4, and in particular it's negative, then the formula is y equals 1/2 of v prime of x, same thing, minus T4x times square root of x squared minus a squared times x squared minus b squared, with a squared equals minus T2 over T4 plus 2 over square root of T4, and b squared is minus T2 over T4 minus 2 over square root of T4. So you see that now the polynomial under the square root has 4 simple roots instead of 2. And it still has a double root, which I could pull out and which is located at 0. If you want, in my picture, in the picture of the plane with the 4 forbidden sectors, typically, for this value of T2, generically, you would have expected something like so for generic values of the parameter which I called C01 this morning, the 6 zeros would have looked like that. And you would take cuts this way. And again, we know that if we take a gamma prime, that gamma prime would be something like the imaginary axis, something surrounding the imaginary axis. The integration contour of W01 has to vanish, which means that this cut must collapse. But these cuts are on the real axis, so there is no reason why you would expect the integral to vanish for these cuts. So there is no constraint. So the only constraint is that this cut has to collapse. So you have one double zero, but not several double zeros. And in this case, you have a square root of a degree 4 polynomial, which is characteristic of a genus 1 curve. So the genus of the curve is genus 1. So when you represent this curve, so if you plot in the xy plane, if you plot this curve, it will start looking like that. Okay, but if you replot it in C cross C, somehow it starts looking like that. And you see that it has the topology of a torus. There is a hole in the middle. It's a surface with the topology of a torus. This curve is a torus. So meaning that instead of having a map from your curve with now 2 branch cuts, this is no longer related, so this is no longer isomorphic to the, isomorphic I mean by a conformal transformation. This is no longer isomorphic by conformal transformation to the complex plane, but to a torus. So typically a parallelogram, 0, 1, tau, where you identify this side on this side with this side. Okay, so you can do a lot of computations with that. If you go to my personal web page at this address, there is a tab called Gallery, and in it there is another tab called Matrice aléatoire potentielle quartique, where you can see an illustration of the transition between the two regimes and how the paths, the location of the paths, the cuts change. And in fact, there is also another story. So I talked about steepest descent paths, which means that there is a kind of unique way to continue the cuts, following some gradient to infinity. And what you should make sure at the end is that when you do that, the steepest descent path that you get is the real axis. Otherwise, it means, again, your hypothesis was wrong. But so I did that. I did that on this page, and I can try to show it to you. I don't know if it's so visible. So here, let me try to enlarge. Okay, that's the. Okay. Here, this is the density. Here, this is the density, and here it's these two sliders correspond to the value of T2 and T4. And when I move T2, so when T2 is becoming more and more negative, you see that there are indeed two cuts. There are two regions where you have density of eigenvalues. This corresponds to this regime. And when T2 reaches the critical value, you have this square root vanishing of the density, and the two cuts merge, and it does that. Now, if you follow this picture, in fact, the red line is the locus of the cuts, and the lines between the blue and the green and all that are the steepest descent paths. And what you observe is that at the transition, they change topology. And, well, you can play with that. And you see the change of topology. So here we have one cut. And here we have two cuts. Okay, you can play with that, but it is basically just using these equations. Sorry? Oh, sorry. So here you see the density. So we are in the regime with two cuts. Okay, and here the two red lines correspond to the two cuts. And again, I was saying that the frontiers between the yellow, green, blue are steepest descent paths. Okay, and when you move the value of T2 at some point, the two cuts merge, and you see the density as exactly vanishing at 0. And above the critical value, you have a one-cut situation. It looks like this picture. And you have one cut, and the topology of the homotopy classes of the steepest descent paths has jumped. There was a Stokes phenomenon. Okay. Yeah. Okay. So, okay, I mean, there is a whole theory of how to know if you have found the correct density, the correct spectral curve corresponding to your potential, to the specific values of T2, T4, and so on, and your path, gamma, and so on. There is a complete, there is a big literature and corpus about that, but that's not the purpose here. I just wanted to show you that you can get, indeed, any genus, okay, and you should be able to work in all situations. But what really matters now is that we have obtained a certain algebraic curve, either written as a polynomial equation or its solution, doesn't matter, but we have a certain algebraic equation associated to our initial problem. So we started, so again, to illustrate the idea of mirror symmetry, we started with a potential, and we end up with an algebraic curve, whose coefficients involve this gamma, which contains some square roots and so on. I mean, they are some functions of the initial parameters, T2, T4. They are some kind, well, not so complicated, but still complicated functions of T2, T4. This is the mirror map. And you have a mirror curve corresponding to this potential. So, to your... Right. Now, yeah, a few words about generalizations. Okay. I will just give you the trick of how to find, in general, the genus 0 case. And this probably is something else that I will propose as an exercise. So the general case, so more general, consider the case where v of x is sum of, tk over k, x to the k starting from, let's say, 1 to, let's say, a maximal value, which I call d plus 1. So v prime of x will be sum from k equals 1 to d plus 1 tk x to the k minus 1. Okay, it's of degree d. D is the degree of v prime. Okay, and so I told you that the equation usually will be something like y squared minus v prime of x, y plus p01 equals 0, where y equals w01 of x. And degree of p01 equals d minus 1. And in fact, you also know the leading coefficient. Well, the leading coefficient of p01 has to be the same as that of v prime. And now there are many coefficients that you don't know in p01. So, so p01 must be t d plus 1 x to the d minus 1 plus, and all the other terms, you don't know them. And how many of these do you have? You have d minus 1 terms, possibly. Of degree smaller than, strictly smaller than d minus 1. You have d minus 1 unknown terms. It turns out that d minus 1 yes, is also the number of no, okay. It's also the genus, in fact, as we shall see. In fact, the genus of that curve will be typically d minus 1. And it turns out that the number of unknown coefficients always matches the genus. It's not an accident. So there is something that is called Newton's polygon. So basically this equation, let's write it as p of xy. It's a polynomial in two variables, and I will write it sum of pij xi yj. And in z cross z, in the ij plane, I will put a dot in z cross z every time there is a coefficient pij. So typically we have a y square, so we have a point there. We have y times v prime of x. So at j equals 1, we have all the terms between from x to the power 0 to x to the power d. Okay, possibly. And then the last term has power as it goes up to d minus 1. Okay, so and let's draw the convex envelope. Let's draw the convex envelope. I'll let you check that the number of interior points is equal to d minus 1. Well, it's called the Newton's polygon on the theorem, which goes back to Newton. Is that basically the genus of this curve is the number of interior points, generically. Unless there is some accidental collapse of some, I mean, some cuts have accidentally collapsed, but somehow the maximal genus is d minus 1. Okay. And another thing you can check is that the interior points, when you shift them by the vector -1, -1, they are exactly falling on this here. Or if you want, the interior points are the correspond to all the terms in this polynomial that you shift by the vector 1, 1. It's always the case. I mean, it will always be the case. So which means that, so the genus of such an algebraic curve is d minus 1, or I should say less or equal to d minus 1. So which means that generically, you have d, typically you will have d cuts like that, d of them. And this can be mapped to a Riemann surface of genus d minus 1. Okay. There is a conformal map from this to a genus d minus 1 curve. Yeah. And on a curve of a certain genus, you have some non-contractible cycles. And you have d minus 1, typically, cycles. I mean, typically so let me call it G, the genus, like that. On a genus G curve, you have 2 times G non-contractible cycle. And let's call them A1 up to AG, and let's take a symplectic basis with intersection B1 up to BG. And on this picture, A1 is here, A2 is there. In fact, you would like to call that A3, but in the first plane, A3 is in fact can be obtained by moving the A1 and A2 to infinity and closing back to A3. So in fact, A3 is just minus A1 plus A2. So it's not independent. And the B cycles mean that you should go to the other side of the, so the B cycle would look, so this is B2 and this is B1. Okay. And so now if you write that, so if you fixing the values integral over AI of y dx. So if you fix these values, let me call them epsilon I. In all my framework, they are equal to h bar and I. Well, forget that for a moment. But if you fix these values, since the number of constraints you do by doing that is exactly the same as the number of unknown you have in your P01, basically this determines your P01. So P01 is determined by fixing the values. So it's more or less, so it's a little bit the same I was saying before. If you want to have your values on, if you want to have 100% of your values on the real axis, it means that one of these integrals has to be 1 and the others have to be 0. And that obliges some cuts to collapse and so on. But the general idea is that the number of unknown in your P01 matches exactly the number of such contours. And these contours are in one-to-one correspondence with your gammas you started with at the beginning. So this is, but now, now let me consider the situation. I don't want to raise that immediately, so let me keep that for a moment. I want to consider the situation where you are lucky and in the end your curve will be genus 0. Case genus 0. So, which means there exists a rational parametrization. And typically, your rational parametrization will always be that x is some rational function of z, y is some rational function of z. Because there are two sheets, or if you want, the degree of this polynomial in y is degree 2. There are two sheets, which means that for each x should correspond to exactly 2 points on your Riemann surface. For each x, there are 2 points on your Riemann surface, which means that the rational fraction that you have to use here must have degree 2. And a rational fraction with degree 2 could be, for example, a polynomial of degree 2, or it could be a rational fraction with 2 poles. Or if you want, there is either a double pole or two different poles. In fact, these 2 poles are clearly distinct, so it must be something with 2 distinct poles. And up to reparametrizing the variable z, let's say one is at 0, one is at infinity. And so you have z plus 1 over z. In principle, they could have different residues, but Mobius transformation have 3 degrees of freedom. So we can make that they have the same residue, and we call it gamma. And we could still add a constant. Let me call it alpha. In fact, in the even case that I considered so far, alpha was always 0. And y must be a certain rational fraction of z. For the same reason I explained this morning, it must clearly have poles only so it cannot have poles in the upper sheet. It can have poles only at infinity in the lower sheet, so which means only at z equals 0 in this picture. So it must be sum over u j z to the minus j equals 1 to, and since y has the same degree as v prime, so d. So you must look for a solution that looks like that. And we know that when z goes to 0, we know that y should behave like v prime of x plus O of 1 over x when z goes to 0. And that will fix the values of all the uj's of gamma and alpha. Well, in fact, we know something else, is that in the physical sheet, y behaves at infinity as, so it was t over x, but here t equals 1. So 1 over x. This is how you find the solution in general. If you know in advance that your solution is going to be genus 0, you can do that. What you can do also is try a solution of genus 0 and see if you get a positive density of eigenvalues that is with the correct steepest descent contour and so on. That, I mean, you can just make it an ansatz and try it. Zhukovsky. And in fact, I'm not sure how you, because it's a Russian name, I'm not sure how it should be written. Maybe there is some Russian who know how to write Zhukovsky here. Yeah, Zhukovsky. Okay. Why? Okay. Yeah. I don't really speak Russian. So. Okay. Yes. So, so in fact, the trick. So let me show you how it works for the quartic potential. So just write that v prime of x is so it's t2x plus t4 x cubed. So let me write it as t2 gamma z plus 1 over z plus gamma 1 over z plus alpha plus T4, and we have gamma cube z cube plus 3. Well, let me start working with alpha equals 0. It will simplify things greatly. Plus 3, well, T4 gamma cube z3 plus 3z plus 3, 1 over z plus z minus 3. Okay, and basically, this constraint is going to say that the negative powers of z should match on the two sides. So basically, we read immediately that y is going to be T2 gamma over z plus T4 gamma cube over z cube plus 3 T4 gamma cube 1 over z. So I just read it from there. Now I want to see that when z tends to plus infinity, y should behave as t over x, which means t over gamma z. So you just identify t over gamma must be the quotient of 1 over z, so it must be equal to 2 gamma plus 3 T4 gamma cube. This is my equation here. So you see, when you use this method, it's really fast. And it works for potentials of arbitrary degrees. If your potential is not even, you should not assume that alpha equals 0. Even if your potential is even, by the way, there can exist some solutions with alpha non-zero. Another thing I wanted to recall before going further is for the equations. For the loop equations, I wanted to recall something. So, for example, I gave you the, so remember that z was 1 over n factorial, integral over my gamma of Vandermonde of lambda to the square, d lambda 1, d lambda n, exponential minus 1 over h bar, sum of v of lambda I and v of lambda I, sum from I equals 1 to n, and sum from k equals 1 to d plus 1, tk plus tk over k, lambda I to the k. Okay. What is, let's compute d over dtk of log z. Okay, so when you do d over dtk of log z, you will find basically 1 over z times this integral, and basically d over dtk will put down 1 over h bar, sum over I, 1 over k, sum of lambda I to the k. And it will be the expectation value. So in the end, just see that it will be minus 1 over h bar, 1 over k, expectation value of trace of lambda k. If you take sum over k k times d over dt k and multiply by 1 over x to the k plus 1 and multiply by minus h bar. Okay. You take this operator, you apply it to log z. What you get is expectation value of sum over k, 1 over x to the k plus 1, trace of lambda k. Well, in fact, to be complete, let me put an additional exponential minus h bar, minus 1 over h bar, n times t0. Basically, just I add a constant term to a potential. And here, okay, for k equals 0, I should do something special. Well, the idea is that I would like to start with t0. Okay, let me be a little bit sloppy here. I mean, you can complete the details. But basically, this is what I wanted to say, is that this is the resolvent, trace of 1 over x minus lambda. And this is W1 of x. Let me give a name to this operator. Let me call it delta x. Well, you remember that, in fact, when I defined, okay. Okay, later I will want to multiply it by dx to make it a differential form. Okay, for the moment. So let me consider this operator. So you see that when I act with this operator on log z, I create one resolvent. If I act another time on log z, I will put another trace of resolvent inside. So basically, if I write dx1, dx2 acting on z, and I divide by z, I will have the same kind of, what I will get is expectation value of trace of 1 over x1 minus lambda, trace of 1 over x2 minus lambda, which is the function that I call w hat, w2 hat of x1, x2. And so on. I can repeat that. So this operator is often called the insertion operator. Right? If you want to compute not W2 hat, but W2 to get the cumulant, you should subtract to that the product of two W1s. And this is exactly what the same operation as acting with the two deltas on the log, turns out. So if you do now delta x1, delta x2 on log z, then you will get W2 of x1, x2 without the hat. You get the cumulant. And in general, delta x1, delta xn acting on log z will give Wn of x1, xn. Okay, this is kind of convenient. Now, remember you had these well, what I'm going to talk about, I don't remember what was the numbering, but loop equations and Vira-0. So now, remember what were the loop equations. Typically, we got that expectation value of trace of lambda k b prime of lambda, h bar minus 1, minus sum from L equals 0 to k minus 1 of expectation value of trace of lambda j, lambda L, trace of lambda k minus 1 minus L equals 0. As I just showed you, an expectation value of a trace is the same thing as acting with a d over dtk. A moment, trace of lambda k, is such an expectation value. And for example, now if you apply d over dtk1, d over dtk2, you will get h bar minus 2, 1 over k1, k2, expectation value of the product, trace of lambda k1, trace of lambda k2. So basically, I'm going to retranslate these equations into some differential operators acting on z. And let me give you the formula. Let me introduce these operators. Well, LK. I hope I didn't get it wrong. Sum, so h bar 2, sum from j, L equals 0 to k minus 1, j, k minus j, d over dt, j, d over dt, k minus j. So basically it's going to be that one, but somehow I change k to k plus 1 here. Let me put a k plus 1, k minus l. And let me recall this j. Plus sum over j equals 1 to infinity, k plus j, tj, d over dt, k plus j. Okay, and to be rigorous, I also need plus k, d over dtk, d over dt0. I hope I didn't get it wrong with and this is really for k larger than 1, I think. There is a formula for L0. There is a similar formula for L0 and L minus 1, which is just a way to solve the issue of the bonds. L0 is, okay, let me not be rigorous about the powers of h bar. Minus sum from j equals 1 to infinity, j tj d over dtj, and n minus 1 is t1 d over dt1, minus sum from j equals 1 to infinity, j tj plus 1 d over dtj. I write j equals 1 to infinity in each of these cases, but remember that only finitely many tj's are not 0. So in fact, it's a finite sum. You can easily compute that these operators satisfy the Virasoro algebra, LK, LJ, or the positive part, which is called the De Witt algebra. So they satisfy Virasoro relations, these operators. Or De Witt. You can define T of x as the sum over k of 1 over x to k plus 1, k larger than minus 1, 1 over x to the k plus 1, lk. It is an operator, but it depends on the variable x. In fact, it's a quadratic differential operator. You should multiply everything by dx squared to have it well behaved. Well, let me not do it at the moment. But under changes of variables, it behaves like a quadratic differential.
That T1 dt T1, right? That process in L minus 1.
I can't read my notes, but probably it's wrong.
That should be DDT naught.
Yeah, it's probably DDT naught. I think so. Okay, you're right. But it's easy to, I mean, you can try, and it's written in many places. It has been used a lot by the physicists in the 80s, and so this is written in many, many places. And these commutation relations can be written the following way: T of x, T of y is d over dx minus d over dy of acting on the function t of x minus t of y over x minus y. And another nice property is that, so I started by introducing this operator delta x, but let's write it as d over dx of an operator that I will call dx. And so dx is the operator sum over k, 1 over x to the k, d over dtk. So it's the primitive of delta x. Okay? And you have some nice relations as well that are that t of x commuted with dy is minus dx minus dy over x minus y. Okay, and the loop equations yes. Okay, and the loop equations can be written in this way. Yes. The loop equations which I have, which are up there, can be written with this insertion operator in this way: delta of x to the square minus v prime of x dx applied on z, divided by 1 over z. It should be this. It should be a polynomial of x. Because you see, delta x. Delta x acting twice on z gives this w2 hat of xx minus v prime of x w1 of x. So there is an h bar. No, the definition of h bar was in the delta. Well, basically, and it's going to be our p1 of x minus p1 of x. No, there is no h bar minus 1. Yes, there is an h bar minus 1. Okay, it was just to show you that you can relate the loop equations to some Virasoro constraints. And also a way to write the loop equations is that there is a certain operator made of these insertion operators that acting on z, that acts linearly on z. And this is a set of linear constraints. I didn't write, so there is in fact a formula that always works for the right-hand side. I'm not going to write it. Yes, okay, the last formula I forgot to write is that indeed t of x is delta x to the square minus v prime of x delta x plus h bar minus 1 v prime of x delta x and plus, so the polynomial part, which is just rewriting this. Okay, now let's move to something else. Let's start now. Okay. The next part is now higher WGN. So far, we found W01 of x, which is solution of an algebraic equation of a type. So if you call it y, it's solution of an algebraic equation of a type p of xy equals 0. And here in this case, this is y squared minus v prime of x y plus p01 of x equals 0. Now let's find the other ones. The next one that we shall compute is W02. What we can do is write the loop equations, try to find a loop equation that can determine W02. And if you remember the loop equations I wrote this morning, there is one that will do the job. So the equation that I wrote this morning was 2W, it was W3 hat of x, x, x2, let's call it this way. So what we want is to compute W02 of x1, x2. And for the moment, let me call x equals x1. It will spare some time. Plus d over dx2 of w1, of x minus w1 of x2 over x minus x2 was equal, I think, to p2 of x x2. No, sorry. Minus, so it was equal to v prime h bar minus 1 v prime of x w2 of x x2 minus h bar minus 1 p2 of x x2. And p2 is a polynomial only in the first variable. So again, we use the asymptotic expansion, and we should expand W3 hat into its cumulant. And let me tell you what you get. Sorry, here it's a hat on the hat. When you expand everything in terms of cumulant, what do you get? You get that 2 W1 of x, W2 of x x2 plus W3 of x x2 plus d over dx2 w1 of x minus w1 of x2 over x minus x2 equals v prime of x w2 of x x2 minus h bar minus 1 p2 of x x2. I removed the hats and I subtracted the fact that we already had an equation, the loop equation for W1, and this is what remains. This is an exercise. to go from the hat to non-hats. Okay, you see that W3 hat will also contain something like W1 of x times W to the square times W of x2 times W1 of x2. But so somehow it completely decouples x and x2. And here also you have a W1 of x times W1 of x2. And using the fact that you know the equation for W1, all these terms go away. And basically, the only ones that don't go away are the ones where x and x2 appear in the same, inside some, I mean, are together in a function. All right, so this is the equation. So now we use topological expansion. We know that this one is of order h bar in the, this one starts with an h bar 0, and this one starts with an h bar to the power 1. And, sorry? No? No, because in this one, you removed W1 of x, W1 of x2, and also this, the P2 is the cumulant of the P2 hat. All right. So, so what is the leading order of this equation? You see that to leading order, you don't have to worry about W3. W3 will start to appear only at next to leading order. So to leading order, what this equation becomes is 2 times W01 of x that we know, W02 of x2 that we don't know, plus d over dx2 W01 of x minus W01 of x2 that we know over x minus x2 equals v prime of x W02 of x2 that we don't know minus p02 of x on x2 that we don't know, but we know it is a polynomial of x. So basically we can, well, W01 is known, p02 is not known, but it's a polynomial of x, and basically that's almost allows to find W02. In fact, solving this equation is very tedious, given the fact that I will show you the solution in a minute, which is totally, I mean, the solution is much simpler than the equation. And so let's take the genus 0 case. And remember that W01 of x could be written as this y of z, with x being equal to gamma z plus 1 over z. And this one was, let's say, in the quartic potential, it was, so I remember, so in the quartic potential, it was 1 over gamma z plus T4 gamma cube over z cube. Okay, on similar expressions. Do the same thing with x2. Write x2 equals gamma z2 plus 1 over z2. Okay. Play a little bit, and you will find the following thing: the 0 to of x, x2. What you will find, I will show you the solution, but just it's useful first to remember that dx is gamma times 1 minus 1 over z square dz, and dx2 likewise is gamma 1 minus 1 over z2 to the square dz2. So let me multiply by dx and by dx2 and rewrite everything in the z variables. So let's write everything in the z variables. And before that, I also would like to add plus dx, dx2 over x minus x2 to the square. So in the z variable, you guess that there will be a pole at z equals z2. A double pole at z equals z2, because I did add this term. There could also be a pole, so since I introduce here a double pole at z equals z2, at x equals z2. There are two possibilities, either z equals z2 or z equals 1 over z2. So there could be also a pole at z equals 1 over z2. But in fact, when you do the computation, you realize that no, there is no such pole. But you have to work a little bit hard. And in the end, I tell you what is the solution. Z minus z2 to the square, dz, dz2, and that's it. So again, I was saying, so you could deduce this from the equation, or check that this satisfies the equation. But in fact, there is a kind of general principle. This will be the case it's totally independent of being quartic potential. It works for all potentials in genus 0. And in fact, it works also in higher genus. The only thing is that here you have to replace this by the kind of elementary function on your Riemann surface that has a double pole or no other pole. And it's kind of canonical. And some people call it the Bergman kernel. So the general result is the following. W02 of x, x2 plus, so dx, dx2 plus dx, dx2 over x minus x2 to the square. And by the way, observe that this expression is nearly the same than here. And in fact, because this is this elementary, well, it's called the canonical fundamental, it's called the fundamental bidifferential of the second kind. But this one is in the x variable, this one is in the z variable. So this one was in the x plane, and this one is the one on the full Riemann surface, whereas this one was only in one sheet. And the right-hand side, let me call it B of Z2. And it is a bidifferential. So by the way, this product of differential is a tensor product. It's not an exterior product. Which means it's a one form in the Z variable whose coefficient is a one form in the Z2 variable. Which means that when you do integrations, you can integrate one, then the other. Okay. They live on two copies of a curve. So this is a bidifferential, bilinear differential. It is symmetric. So it is equal to B of Z2Z. And it has a double pole at coinciding point. Which behaves in this way, and no other pole. On the Riemann sphere, this is unique. This completely characterizes this object. You can observe that this is invariant under Mobius transformations. If you change, for example, z to 1 over z, you will realize that this is invariant. Z to z plus a constant is invariant, and if you rescale z, it is invariant too. On higher genus Riemann surface, it is unique if, again, you fix the A cycles. In the world of topological recursion, people have started to call it the Bergman kernel. And I think it's a little bit, well, it's at the same time a good and bad name. I will tell you the reason. It's that, well, in fact, I mostly took the name from, so I think, so in fact, this thing appeared already in papers by Riemann, in the works of Riemann, and Riemann called it the fundamental differential of a second kind. So he called it fundamental bidifferential of second kind. Second kind refers to the fact that it's a double pole. On fundamental, because Riemann was already aware that this is one of the most important objects on a Riemann surface. In fact, I think really all the geometry of a Riemann surface is encoded in it. It's also very closely related to what people call the green function on the surface. And in fact, this is nearly the second derivative of the green function, or to be precise, the green function is a real function. And if you take the real part of the second derivative of that, basically you recover the green function. Sorry. To have a green function, you need to integrate with respect to z, integrate with respect to z1. So you take the primitive in both variables. Typically, it will behave like log of z minus z2. And then you take the real part, and this is basically your green function. There is a lot of nice electrostatic interpretations on that. But so it's a very important object on the Riemann surface. And it turns out that in random matrices, W02 is always, modulo adding the Bergman kernel of the X variable, it's always the Bergman kernel of your Z variable. So now why is it called Bergman kernel? In fact, there are really a lot of works of Bergman on this kernel. Bergman has really worked a lot on this kernel. He has even written a book, I think, on it. However, Bergman is more known for another kernel. So, in fact, he has worked on both. But so, what people in operator theory call the Bergman kernel is not this one. However, I think this one could deserve really to be called Bergman kernel because the person who studied it most is probably Bergman with Schiffer. So sometimes you associate the name of Schiffer on Bergman. Schiffer was, I think, the student of Bergman. And so it's, and there is a book by Bergman and Schiffer on it. And it's a very, very important object. And Korotkin started to associate an integrable system on a tau function to this kernel. And he called it the Bergman tau function. And he had a lot of works on that. And basically, I borrowed the name from Korotkin before realizing that it was not the Bergman kernel that everyone else was calling in operator theory. But I think first it would deserve to be called the Bergman kernel. Fundamental bidifferential of the second kind is very long to say, but it should be the name. Okay, so whatever. Just to give you a hint of what happens on other Riemann surfaces for people who have knowledge of, let's say, elliptic curves. On an elliptic curve, on a torus, there is a function that has a double pole and no other pole. It is the Weierstrass function. So you should replace 1 over z minus z2 to the square by Weierstrass function of z minus z2. And it exists on every Riemann surface. It's also equal to the second derivative of a log of a theta function. And there are plenty of formulas. There is even a combinatorial formula to find this Bergman kernel from the coefficient of your algebraic equation. I mean, there are plenty of formulas to find this kernel. But the idea is that you never want to solve this equation. Just use the result. Okay? So now, let us consider that W02. So let me put something here. W01, done. W02, let's consider it's done. Now, what shall we do next? I think we should do W03. Or no, let's start with W11. Except that for W11, I will not finish the full computation to the end. But let's remember what was our equation. I recall our equation, W2 of xx plus W1 of x to a square was equal to h bar minus 1 p prime of x W1 of x minus h bar minus 1 p1 of x. Now, again, we use that leading order, so I should have written it in the other way. W1 of x to a square plus W2 of xx. Okay, let's start by the leading order. So the leading order was h bar minus 2 W01 to the square. Then the next tooling order was 2 W01 W11 plus, well, the next term will be 2 W01 W21 plus W11 to the square, sorry, h bar square plus O of h bar 4, okay, plus W02 of x plus h bar square W12 of xx plus O of h bar 4. And on the right-hand side, we shall have h bar minus 2 v prime of x W01 of x minus P01 of x plus v prime of x W11 of x minus P11 of x plus h bar square v prime of x W21 of x minus P21 of x, and so on. Okay. I'll let you continue. So the order h bar to the minus 2 is done. Okay? So next tooling order, what do we get as an equation? We get that 2W01 W11 plus W02 evaluated at xx equals v prime of x W11 of x minus P11 of x. We know W01, we know W02, so W11 of x is v prime, let me write it this way, v prime of x minus 2W01. No, let me write it the other way around. 2W01 of x minus v prime of x. Well, so there will be a minus sign, minus W02 of xx minus P11 of x. All right, so it's almost, okay. We almost know what it is, except that we don't know yet what is P11. We know that P11, so let me go back to our example of quartic potential. Well, the degree of P11 should be less or equal than the degree of V prime minus 1. But if you pay attention to, and so remember that P1 of x was V prime of x W1 of x plus, and so it means that it was V prime of x W01 of x plus V prime of x W11 of x, so h bar square, sorry, h bar minus 1, h bar plus O of h bar cube. So this one is P01, and this one is P11. There is something important to realize, is that we knew that W1 of x behaves when x goes to infinity as 1 over x plus, let's say, expectation value of trace of lambda to the x square. Sorry. N. Okay. So, but you see that this term, so let's multiply by h bar. This term is 1. And so the leading coefficient does not depend on h bar, which means it will appear here, but not in W11. So which means that W01 of x behaves at x to infinity as 1 over x plus O of 1 over x squared. But W11 of x should behave at infinity as O of 1 over x squared. Just because the leading coefficient has no h bar expansion. Which means that the degree of P11 is in fact smaller, -2 here. So let's keep this for a moment. We shall need it because W02 appears. And also observe the following. You remember what W01 was on 2W01 minus V prime. It is equal to 2 times square root of V prime square minus 4P01. No, without a 2, sorry. And remember that in the genus 0 case, so let's take the example of genus 0, but in fact, many of the zeros of this polynomial inside the square root were double zeros. We could put them out. And in fact, in the end, we had only square root of x minus a, x minus b, and a certain polynomial, let me call it m of x, which corresponds to all the double zeros. I just want to illustrate. So in general, for higher order genus, that would be less or equal to d minus 1, we would have something like still an m of x, but a square root of product from I equals 1 to 2 times the genus plus 2 of x minus ai. When the genus is 0, you have just 2 simple zeros, and in general, you have 2 times the genus plus 2. The idea, I really want to separate the double zeros and the simple zeros. In the most generic situation, you have no double zeros, and there will be no more constraints. But you see, so what does it mean? It means that W11 of x is minus W02 of xx plus P11 of x over this square root, m of x. Let me call that sigma of x. So it's m of x square root of sigma of x. And again, you have to remember the cycle integrals condition that whenever you encircle, whenever in your complex plane you take a contour gamma prime that encircles a region where you should not have eigenvalues, this should give 0. You see that this W11 has branch cuts at the zeros of sigma, but it also has simple poles at the zeros of m. However, if you think about the example of our quartic potential, the zeros of m were somewhere here. And this was AB. So in our example of the quartic potential, we had zeros there on AB. And gamma prime can be taken here. Which means, and so the circle integral of W1 or this gamma prime should be 0, which means that the circle integral of W11 over this gamma prime should be 0. Since this is a simple pole, it means the residue must be 0 at this simple pole. So it means that the P11 should be exactly such that so exactly at the 0 of M, it will be exactly equal to minus W02 at these points. And if you think about it, there is exactly the same number of zeros. M has exactly, so in the genus 0 case, M has exactly the same numbers of zeros as the number of unknown coefficients in P11. And again, this totally fixes P11 in the genus 0 case. In higher genus case, you have to fix, in general, this is fixed by filling fractions. And again, the number of unknown coefficients in P11 matches exactly the number of contour integrals that you can fix. Okay, this is kind of technical. I don't want to enter the details, but basically the idea is that P11 is again totally fixed by this kind of filling fraction conditions. And in the genus 0 case, this is the unique choice that will kill exactly all the zeros of M. So since you know the value of P11 in a certain number of points, you could use, in principle, Lagrange interpolation formula to reconstruct P11. Since you know its value at certain points, you could use the interpolation formula, recover it, and so on. There is one way to use to write the interpolation formula. It's by writing residue formula and so on. But the idea is that I just wanted to show you that there is a way to find P11. But there will be a shortcut again, and we shall take the shortcut. So the idea is that P11 of X is fixed by filling fractions condition that say that basically integral over W11 of X dx over some A cycles should be some in fact, should be 0. And basically, that fixes P11. And in the genus 0 case, W011 of X must have no pole at zeros of M of X. This is more or less the same condition. And you can find it. Now, again, to find it, we shall use the Z variable. And we shall rephrase all these properties in the Z variables. And in the Z variable, the solution will again be much, much simpler. So use Z variable. So let me again consider the case where X equals gamma Z plus 1 over Z, and Y was T4 gamma cube Z cube plus 1 over gamma Z. So this is the case that we illustrate. I just finished writing that and I answer your question. Now I will put this data also in the notion of spectral curve. Well, in fact, these are simple poles. I mean, M, well, generically M has simple zeros. So the poles are simple, so it's equivalent to say the residue is 0. But so let's take this spectral curve to illustrate what I'm saying, but what I'm going to talk about works just in general, but let's take an example. In this example, so basically we shall use the Z variable, or first of all, sigma of X in this language is square root of x squared minus 4 gamma squared. And if you use this parameterization, it's just gamma times z minus 1 over z. Another thing which is very useful is that dx is gamma times 1 minus 1 over z squared dz. Just take derivatives. Which means that, well, you see that at some point you have to compute W02 of x. W02 at coinciding points. Well, you see you have to take the subtraction of these two things. This has a double pole, this has a double pole, so you need to expand to second order. It's a little bit tedious. It's called the Schwarz derivative, by the way, to do that. Taking the Schwarz derivative. But so when you compute W02 of x on x, it turns out, if you use this formula here, it turns out that, well, no, okay. Let me show you a kind of miracle. So first, observe that x of z is the same as x of 1 over z. Trivial, if you exchange z on 1 over z, it's invariant. And let us compute b of z, z2, plus b of 1 over z on z2. Exercise, do the computation, but what you will find is that it will be dx dx2 over x minus x2 to the square. In other words, W02 of x, x2 times dx dx2 was equal to this minus this. So it was equal to minus b of 1 over z on z2. Which also means that W02 of x, x2 was minus b of 1 over z on z2 divided by dx divided by dx2. Let me compute it in more detail. So this was d of 1 over z times d of z2 over 1 over z minus z2 to the square. And you divide by dx, which is gamma 1 minus 1 over z square dz times gamma 1 minus 1 over z2 square dz2. D of 1 over z is minus dz over z square. Well, in the ratio, the dz cancel, the dz2 cancel. So what do we have in the end? We have a minus, minus, so it's a plus. We have 1 over z square, 1 over z minus z2 to the square, times 1 minus 1 over z square, times 1 minus 1 over z2 to the square. Or gamma square. Which leads us to W02 of xx equals 1 over gamma square z square 1 over z minus z to the square times well, in fact, I will multiply this 1z here and 1z here, and when I do that, I just get back to the 4. Okay. The only thing I want to see is that there is a degree 4 pole at z equals 1 over z. So there is a degree 4 poles at z equals plus or minus 1. So pole at z equals plus or minus 1. which, if you remember, was x equals plus or minus a. So basically at the extremities of a branch cut. So this has poles at the branch points, and nowhere else. So let me put this here. Let me multiply everything by dx. So this will be minus, so 1 over gamma square, 1 over z minus z to the 4, times square root of sigma. So in this case, square root of sigma was gamma z minus 1 over z, but dx, let me write it in this way. It is gamma z minus 1 over z times dz over z. So dx over square root of sigma, sorry, this was square root of sigma here. Dx over square root of sigma is just dz over z. So dz over z times 1 over m of x of z minus p1 1 of x dx over m of x gamma times z minus 1 over z. Well, again, dx over that is equal to dz over z. What did we learn by doing that? We learned that this expression will probably have poles at z equals plus or minus 1. We know that at z goes to infinity, we know that at z goes to we learn another thing, by the way. It is if you exchange z on 1 over z, so if you exchange the sheets, it just changes the sign. So everything that we know in the upper sheet will translate immediately in the lower sheet. Can it have a pole at z tends to infinity? I recall that at z tends to infinity, w11 of x should be like 1 over x squared. Even when you multiply by dx in the z variable, this means there is no pole at z equals infinity. And by exchanging the two sheets, it means there should be no pole at z equals 0. And we know that, so basically, what are the possible poles? We can have poles at z equals 1, z equals minus 1, no pole at infinity, no pole at 0, no poles at the zeros of m. Basically, it remains only 1 and minus 1. So the only thing that we can get at the end is sum over epsilon equals plus or minus 1. So the only thing that we could get in the end would be dz times some expression that could have poles with, let's say, z minus 1 to the 4, well, some coefficient, well, plus something with z minus 1 to the 3, plus and so on z plus 1 to the 4. Okay, z plus 1, some coefficient with z plus 1 to the 3, z plus z minus 1 to the square, z minus 1, z minus plus 1 to the square, z plus 1. Yeah, we cannot have constant terms because it must go like 1 over z squared at infinity. Well, so in general, so basically the shortcut that I told you that we are going to take is just that. Identify where the poles can be. The only poles can be there. And now let's put that, let's use a trick, which is just Cauchy residue theorem. And this will be really, how much time do I have left? I'm really arriving to, okay, I'm really now arriving to the topological recursion itself. So you will see the formula will pop up very shortly. So remember that after multiplying by dx, this is what I call W11 of z. So now let me consider it a differential form on the full Riemann surface. So it means in the z variable. So we want to compute W11 of z. So it is dz times the rational fraction of z, and we know that the only poles can be at plus or minus 1. But, so let me divide it by dz, then it will be, so I will remultiply after. Then this is a rational fraction of z. And let me just say that it is the residue when another variable, let's call it z prime, goes to z of 1 over z prime minus z times omega 1 of z prime, and again, to make it a function, I divide by z prime, but to make it, remember that the residue is a differential form, so you should put the dz prime. The miracle is that the dz prime goes away. I mean, somehow omega 1 contains the dz prime. So this is simply Cauchy residue theorem. Let me remultiply everything by dz. But this is not the integration variable of the residue. It's just because you want to make a differential form. So don't be surprised in many of my lectures, and some people find it really strange. I write it this way, dz over z prime minus z, omega 1 of z prime. But this is not the integration variable, this is a kind of constant. Okay. Now, now we shall move the integration contour. Because where are all the poles? So you know that there is a theorem saying that the sum of all residues has to be 0. So this has to be equal to minus the residues at all the other possible poles. What are all the other possible poles? Well, clearly here, we already took the pole at z prime equals z. Where can be all the other possible poles? The other possible poles, we know that there is a pole at z prime goes to plus 1 and minus 1. We know that W11 of z prime at infinity behaves like 1 over z prime square times dz, and there is an additional even 1 over z prime, so it's a 1 over z prime cube. So there is no pole at infinity. There is no pole at 0. In fact, there is no other pole. So that's the only poles. dz over z prime minus z, omega 1 of z prime. That's the only poles. Okay, so far so good. This was kind of trivial. Let me replace that z prime goes to plus or minus 1. dz over z prime minus z. And now, let's use this expression. So I will replace W11 of z prime by this expression. And let me remind you what, so W02 of, sorry, and we have this dx here as well. So W02, let me recall that W02 of xx. I remind you that this was b of z and 1 over z divided by dx, so, sorry, the minus sign, dx of z, dx of 1 over z. And this one is the dx of z. And m square root of sigma was this guy, m square root of sigma. So here we have m square root of sigma. Here we have our b of z on 1 over z minus, sorry, I have several minus signs. So we have a minus here, a minus there, and a minus there. So in total, this is a minus. But then we'll have plus, I think, p, so times dx of z on dx of 1 over z, and times the dx of z. And let me write the other term. The other term will be plus p11 of x dx of z over m of x square root of sigma of x. And I remind you that dx of z over square root of dx of z was just dz over z. Right? And well, m square root of sigma, okay, I will write it in a minute. Well, first, dx of z and dx of z cancel. It's very easy to see that dx of 1 over z is the same thing as dx of z. And that I will often call right x prime of z dz. Or sometimes dx of z. But what is the miracle here? Observe the term with p11. P11 is a polynomial of x. It has no pole at x equals plus or minus a. It has, so basically no pole at z equals plus or minus 1. M of x is also a polynomial of x, and by and generically, I mean, it contains all the terms that are not there. So basically, it has no pole, and in the quartic case, it has no pole at z equals plus or minus 1. And also dz over z has no pole at z equals plus or minus 1. So in fact, there is no pole at z equals plus or minus 1 coming from here. So you don't have to compute it. So in the end, what do we get? In the end, let me rewrite it this way. Omega 1 of z equals residue when z prime goes to plus or minus 1. This plus or minus 1 means you should compute the residue at 1 plus the residue at minus 1. Take the sum of the two. dz over z prime minus z. Let me put the b of z on 1 over z here. There is a minus sign. And there is 1 over m square root of sigma times dx. We're almost there. No, yes, this is important. Remember that y of z was 1/2 of b prime minus square root minus m square root of sigma. Changing z to 1 over z does not change x. So it does not change v prime. It does not change m either. But it changes the sign of a square root. So y, when you evaluate it at 1 over z, it's 1/2 of v prime plus m square root of sigma. Which means that m square root of sigma can be written as minus y of z minus y of 1 over z. Okay, just a kind of smarter way to write m square root of sigma. So in the end, W11 of z, and now we are almost at the residue at z prime goes to plus or minus 1 of dz over z prime minus z, 1 over y of z minus y of 1 over z times dx of z times b of z and 1 over z. And this is more or less the final expression. Let me give a name to this kernel. Let's call it k of z prime. And so by definition, it is dz over z prime minus z times 1 over y of z minus y of 1 over z dx of z and let's call it the recursion kernel. I know some people have given it the name Eynard's kernel as well, but okay. But so the idea is that this kernel will give you everything. So in other words, W11 of z equals residue of z prime goes to plus or minus 1, k of z prime, b of z, oh sorry, it was a prime here from the beginning, and sorry, there were primes everywhere. Yeah, here it was, sorry, there were primes everywhere. Well, let's call it x prime. Well, evaluated at x prime. Okay. I mean, the only place where z appears is here. Everything else was z prime. E of z prime on 1 over z prime. And that's the final formula. I showed you for the case of quartic potential, it's totally general. It's not specific at all to the quartic potential. It's not also specific at all to the genus 0. It would work on any genus Riemann surface. When you do that on any genus Riemann surface, you have to be careful because when you move the integration contour, you might get some contribution from cycle integrals over non-contractible cycles, but then you have to use something called the Riemann bilinear identity to see that they all disappear. And in the end, this is the same result you obtain on any genus Riemann surface. And the K is, well, to see what, so on an arbitrary Riemann surface, this does not make sense. This is a rational fraction. The one form y dx makes sense. Y and dx make sense on an arbitrary genus Riemann surface, but this one does not make sense. And in fact, let me just observe that this z dz over z prime minus z is just the integral from z second equals, sorry, I'm not sure. So I think from infinity to z prime of dz second over z prime minus z second to the square. So it's just the integral from z second equals infinity to z prime of b of z second. Somehow it's just a primitive of b. Also, you should, well, remember that omega 1 is odd when you exchange z on 1 over z. So let me rewrite this, and I will stop. Sorry. So let me rewrite the final formula. The final formula for today will be that you take the kernel k of z on z prime to be 1/2 integral from z second equals 1 over z prime to z prime of b of z second times 1 over y of z dx of z minus y of 1 over z dx of 1 over z. and I'm not sure about the global sign. I hope it is correct. And then omega 1, 1 of z is residue z prime goes to plus or minus 1 of k of z prime, b of z prime on 1 over z prime. Okay, that's all for today. I know this is a little bit tedious, but in the end, you see the final result is much, much simpler than all what you did to derive it. Like omega 0,2, the final result is extremely simple. The derivation was extremely tedious, but the final result is extremely simple. Same thing, omega 1, 1, you see that in the end, the formula is extremely compact, and this formula generalizes to all kinds of problems. And in fact, it goes far beyond matrix models. It works also for, let's say, the Mirzahrani's computation of volumes of moduli spaces. So if basically you take the spectral curve where, so just if you take now x would be z squared, and y would be sine of 2 pi z, 1 over 4 pi times of 2 pi z, you replace the notion of 1 over z. 1 over z was the value for which you get the same value of x. Here you should replace by minus z. So everywhere you have 1 over z replaced by minus z. These points were the places where the derivative of x was vanishing, so replaced by 0. And you will get the volume of the moduli space of Riemann surfaces of M11. Okay. I mean, it's much more general than matrix models. And in the end, the formula is extremely simple. Okay, so. Okay.
First of all, I want to say that it is quite explicit and very impressive combination approach. But I would be much more happy if it would be possible to get all of this, say, from some
First principle?
Like addition theory.
Addition
theory should be behind it.
Yes, yes or no? I can.
There is an explicit formula for genus 1 through Bertrand Eynard.
Yeah.
It means that the relations between this, say, Bertrand function can be used to write.
Oh, of course, yes. Yeah, yes, of course.
You can use your invariants to get this six-term relation.
Yeah, yes, but we do, in fact, yes. And we derive the phi identities. Sorry? Not sure, but you see, this morning I started by introducing these psi functions with divisors, and somehow it's in this direction. I mean, this is the one that will satisfy phi. Yeah. There is an integrable system. Exactly, there is an integrable system, there is Hirota equations, there is phi identities, there is all that. In fact, so this partition function you build from topological recursion will satisfy this. I mean, basically, I mean, I started with matrix models, and it is known that matrix models are isomonodromic tau functions. Yeah. Yes, it satisfies, but it is very non-trivial to prove that. Really very non-trivial. And also, so you were talking about the general philosophy. Now, let me go back to, let's say, counting the quadrangulations. So what we have here is that we see that, you see K, it mostly contains W omega 0,2, so counting cylinders, and Y is omega 0,1, so disks. So you see that this kernel K is made of the cylinders and the disks. And here you get surfaces of genus 1 with one boundary. So if you want the illustration of that, would be something like this. Well, let me put the boundary on the left. This equals the kernel K. Let me represent it as, so you see, it's a kind of cylinder divided by a disk. And let me represent it as it's nearly a pair of points, but there is only two variables. So let's say it's like a pair of points with only two boundaries. And in fact, it's more, in fact, the good representation would be more like it's a pair of points, but with one of boundaries that has been pinched. And B is the cylinder. And Y dx, so omega 0, 1, is the disk. But you see what this relation tells you is that this is the K times the B. And you glue like this. So you see, in the end, this relation is just telling you very simple on how you should decompose surfaces into pairs of points. Except that if you start from the geometry, this is extremely hard to prove. And in fact, what you are doing is you are proving mirror symmetry when you do that. Doing that is proving mirror symmetry. Yeah, yes, there is a mark point, yes. No problem with that. And this is why we take an integral here. It's the mark point. We sum over the possible positions of the mark point when we do that. So from first principle in geometry, it's just gluing pairs of points on cylinders. It should look very, very simple from geometry point of view. In fact, it's extremely hard from the geometry to derive that. And it's not, I mean, Mirzarani got the Fields Medal to prove it for hyperbolic surfaces, and our proof is like 90 pages long. It's really very non-trivial. The fact that it's equivalent to this relation is a few lines proof, but somehow you first need to have proved it before. In all Gromov-Witten, and even for counting triangulations and all that, deriving this from Tutt's equations, I mean, just from the combinatorics is really hard. Somehow, there is no canonical decomposition of surfaces that is known to correspond to that. It's really, so in fact, what we are doing here is proving mirror symmetry. And mirror symmetry is always a very highly non-trivial thing. I don't know any easy proof of mirror symmetry, and in any case, I don't know any really easy proof of topological recursion, which is almost equivalent to mirror symmetry. But so it's always hard to prove, but once you have proved it, it's easy to use. And for example, for Gromov-Witten invariance, you can really, once you know the spectral curve and you know that indeed it is computing your Gromov-Witten invariance, this formula is efficient at computing the Gromov-Witten invariance. Well, it's not the fastest algorithmically, but it's one that will always work. Even if you don't know, I mean, for example, when you can have other methods to compute Gromov-Witten invariance, like holomorphic anomaly equations, but they are not always available, these methods. This one is always available. It's maybe not the computationally fastest, but it's always there. Yeah. Yeah.
It might be very plausible that, for example, for hyperelliptic case, you can also get in hyperelliptic analog condition theorems.
Yeah. Well, okay, we can discuss that in more details, but let me say something. Here, in fact, topological recursion is solving the Virasoro constraints, which are linear, contrarily to the phi identities or Hirota or Yang-Baxter or whatever you want to call them, I mean, integrable systems, which is really non-linear constraints. In fact, topological recursion will give you somehow something which is solution at the same time of Virasoro on the linear constraint, on the non-linear equations. But there are more solutions to Virasoro than the ones that are tau functions. So there is many solutions of Virasoro that are not tau functions. So somehow we get more solutions of Virasoro, and only some of them. Okay, I will not enter the details, but you have either to really choose your spectral curve to get the phi identities, or you have to do something which is the non-perturbative resummation to really get your phi identities. And basically, you have to do it. It's not straightforward, but there is a way to build a solution of phi identities from topological recursion. It's a very non-trivial procedure. I don't think I will have time to, but probably it's what other people in these lectures will talk about. And so, in fact, you don't get directly these addition theorems. On these addition theorems, most of the time, they are still conjectures. They are not proved in all the cases. We know how to prove them in many cases. But let me say that random matrices, which is what we started with, we know that random matrices are tau functions. And we know beforehand, before everything, we know that they satisfy these phi identities. We knew it before. I mean, it's typically theorems derived by meta. The determinantal relations of meta is exactly that.
So if I remember well, to get physicality recursion from topological recursion, you use a kind of a batch transform?
Yes. Well, yeah, exactly. Yeah. Yes, exactly.
So is that like a general phenomenon? Like in the case
yeah.
where
Yes. Yes.
you use that bias?
Yes. Yes. I don't know if someone is going to lecture on that this year, but someone did last year, Gaëtan. Well, yes, but there is, in fact, there is a really actual formula of how to use the Laplace transform to relate the spectral curve to your, typically to cohomology class in a TQFT. So there is really a very, and it's a very, again, compact, simple formula. There is not, but there are experts. There are many experts in the room about this question. Yeah, well.
Yeah, maybe you mentioned that in topological recursion class formulas work beyond random matrices and gave the example of Muscati's volume polynomials. Can you say how you know that that's not going by random matrices?
Well, remember that somehow the discontinuity, so let me call it quote of X here. The discontinuity of Y is going to be your spectral density of eigenvalues. If it were a random matrix model, this should be the spectral density of eigenvalues. And first thing, the sign function changes sign. It's not positive. Second thing, it's not, I mean, its total mass is infinite. It does not, is not absolutely convergent. So it's not a probability density of the type of eigenvalues of a matrix on the real axis. So I mean, okay, you can think of it as somehow very similar to what you would get in random matrix models, but except that you cannot find a random matrix model that has this as eigenvalue density. However, in physics, people call it a matrix model. And in fact, there is a very big activity around that recently, mostly by people around Wheaton, Stanford, and all that. They call it, because they realize that it's related to, I mean, they can compute some black holes, they can find the exact solution of some black hole problem that is called the Jackiw-Teitelbaum black hole. And using this curve, you can find exact solution, and they call it a matrix model. They call it random matrix, although it's a kind of extrapolation of random matrix with an eigenvalue density, which can be negative or, okay. It's kind of analytic continuation of some random matrix. Well, one thing you can say is that you can write sum of tk x to the 2k plus 1, and you see that there are coefficients going from 0 to infinity. And basically, it's 1 over 2k plus 1 factorial times minus 1. Basically, it's something like minus 1 to the k over 2k plus 1 factorial times an appropriate power of 2 pi times 2 pi to the power of 2k or something like that. Okay. Yes, it's something like that. So what did I want? So one thing you could do is truncate this sum to a certain order. And then this will be a random matrix model. And somehow do the analytic continuation. You have to prove that the two limits commute and so on. This is non-trivial, but this is what physicists use a lot. And it gives a lot of result. I mean, if you assume that it works.
Let's thank Bertrand again. The team is from